last time we started a conversation with the discussion of, it's gonna go up in a second. With the we stopped our conversation with the discussion of carbohydrate metabolism, right? And I just want to remind you a few highlights. First of all, 3 steps. We have glycolysis, we have Krebs cycle, and we have oxidative phosphorylation. Electron transport chain oxidative phosphorylation. Second, the main point of glycolysis is to break the 6-carbon molecule of glucose to 2 3-carbon molecules of pyruvate. The major point of Krebs cycle is to completely break down pyruvate to produce CO2, right? And a lot of electrons. Some electrons are produced in glycolysis, but not so much. Got it? And then those electrons, by meaning of NADH and FADH2, the electron carriers, end up in the electron transport chain, where they are oxidized. The electrons go into the electron transport chain. Energy of the electrons is used to pump hydrogens across the membrane. So that pumping creates electrochemical gradient of hydrogen ions. Hydrogens diffuse back across the inner mitochondrial membrane through the ATP synthase, and kinetic energy of diffusion is converted to the energy of chemical bonds in ATP. Now, you can say, oh, come on, we learned it from, I don't know, Biology 1200, high school biology, 1510, microbiology, whatever. A lot of courses that teach it. A very important point that I want to make is that for the future reference, we pretty much couldn't care less about this. I mean, because this is the step where only electrons play a role, okay? At this point, I mean, biochemistry is over. Real biochemistry happens here, okay? This is how we convert glucose to pyruvate. This is how we break down pyruvate. This is where biochemistry exists. So for the future, we're going to be focusing on glycolysis and the Krebs cycle. And we're going to start, so we're now going to look at the metabolism of nutrients. All right? And we're going to start with carbohydrates. And I'm going to, believe me, the questions that I'm going to ask you are going to be very simple. Seriously, no tricky questions. So, I swear. Question number 1. When carbohydrates, say glucose, let's stick to glucose, it's just easier. Glucose is metabolized. It is metabolized in the reactions of glycolysis. Oh crap, let me correct this slide really quick. For shit's sakes. Okay. Just like this. Okay? Just you will see why I do that. Okay? So when glucose is metabolized in glycolysis and Krebs cycle, and then you have oxidative phosphorylation, what is the final product that we are looking for? Simple questions. ATP, yeah, that's what we need, right? ATP, here's the ATP. Here's the deal. ATP is the main energy currency of the cell, yeah. Can we store ATP in the cell? We can't. That's just can't. ATP is not stored. So, what if we have a lot of glucose? A lot of glucose. We can only produce so much ATP. Does that make sense? Do you understand? Now, we can pretty much say that, glucose is indirectly leads to ATP. If you remember chemistry. You have a reaction, like A is converted to B. If you accumulate too much B, reaction is going to stop. Reaction that leads to B. Pretty much the equilibrium shifts to the left. Do I make sense? It actually is common sense. There's a chemical name for it. It's called Le Chatelier principle. But the idea is that if too much product is accumulated, reaction is going to slow down. So if ATP accumulates, and by accumulating I mean it reaches its maximum level, we cannot go beyond it. When ATP accumulates, the reaction of oxidative phosphorylation, reaction of Krebs cycle, all this whole deal, you know, from glycolysis to Krebs cycle to oxidative phosphorylation, this whole process is going to slow down. Does that make sense? Just from the common sense. Okay. So the whole respiration slows down, but ATP keeps coming in. Does that make sense? Since ATP keeps coming in, what do you want to do with, sorry, ATP is at the top, glucose keeps coming in. I'm sorry, I misspoke. Glucose keeps coming in. What can you do with the glucose? Can you store glucose in the cells? Yeah, in the form of glycogen first and foremost. So this is your glycogen synthesis, the purple line. I'm very explicit. I'm not going to ask you about the details and the enzymes. Okay? But you have to understand that elevated levels of ATP will initiate synthesis of glycogen, which is basically a polymer of glucose. Do I make sense? Now, a pretty interesting thing is that, look at this. It requires energy. To make glycogen, it actually requires some energy. Okay? Good? But, say we store glycogen and we store, it's not unlimited. In fact, glycogen storage is pretty, the capacity of glycogen storage is pretty limited. So what are we going to do with glucose when glycogen storage capacity is exhausted? We're going to store it in the form of what? Right? We'll get to the fat storage, but so far you have to understand that high ATP levels will stimulate glycogenesis. Does that make sense? Now, on the opposite side, what if you do not have glucose? What if you do not consume carbohydrates? What if you are starving? You don't have glucose, so it has to come from the storage, which is what? Glycogen, right? So glycogen in the conditions of the low glucose will be broken down to glucose. Do that make sense? Why do we need glucose in the blood? You will see that basically all cells can fairly easily run on ketone bodies. We don't, except for the brain, we don't need glucose. Brain neurons can run on ketone bodies as well, but it's the last resort, really. Do I make sense? It's really the last resort. So, think about this, just kind of recap. So we have a lot of glucose coming in. When does it happen? When? After the meal, we eat something, right? So what's going to be the first chemical pathway to utilize that glucose? The first thing that's going to be done with it. Glycolysis and subsequent oxidative respiration. Does that make sense? Glycolysis goes up. When we have maximum levels of ATP in the cells, what's going to be next? Glycogenesis. Okay? Say you're done here. Now, in the situation when you're starving, what's going to be used as the glucose source first? Glycogen in the process of glycogenolysis. Okay? And then, in the process of gluconeogenesis, glucose will be synthesized from scratch. Am I clear? Now, I mentioned before that one of the main problems with both, explaining and learning physiology is that we always try to break down step by step. And when I tell you this, like glycogenolysis happens first and gluconeogenesis happens second, no. No. They happen at the same time. But when we run out of glycogen, we have only gluconeogenesis. Does that make sense? So it gets kicked up a notch. Okay? Does that make sense? It's always like all processes go, but some of them are more dominant than others, more prevalent than others. Are we clear? I want you to understand what will trigger glycolysis and glycogenesis versus glycogenolysis and gluconeogenesis in terms of ATP abundance, glucose abundance, things like that. Good? Can we move on? We're moving to the fun part, which is lipid metabolism. Lipids are very energy dense. The density is 9 calories per gram of fat, triglyceride, versus 4 calories per gram of glucose. You don't have to memorize numbers. I told you before, I will be explicit on which numbers you have to know. There are very, very few in this course, okay? For instance, I never remember this. Seriously, like every time I tell you this, I read it. I have no idea what the energy density. I have wiki to look things like that. But you have to understand what's going on. So we have lipids that consist of glycerol, which is 3-carbon alcohol, okay? And we have free fatty acids. Okay? So we break lipids down using pretty much water. It's hydrolysis of lipids. You get glycerol and you get fatty acids. Glycerol is 3-carbon intermediate. Let me go back a couple slides. Glycerol is 3-carbon intermediate, so we can plug it in directly into glycolysis. I mean, it's not directly, but glycolysis. Does that make sense? What essentially happens is glycerol converted to glyceraldehyde 3-phosphate becomes the part of the glycolysis reactions and gets turned into the pyruvate. Does that make sense? We're good? With the fatty acids, they are oxidized in the mitochondria in the reaction of beta oxidation. You know, there is a temptation to scare the living daylights out of you, telling you, you will have to know the whole pathway. No, you won't. Here's the idea. Acetyl-CoA binds to the carboxyl group here And then in few reactions, few oxidative reactions, this carbon, the beta carbon, becomes oxidized. So this is what used to be beta carbon. What essentially happens, these two carbons are removed. Okay, these two carbons are removed. And when they are removed, they form a molecule of acetyl-CoA. Okay? That makes sense? Basically what happens, you have a chain of carbons. That's free fatty acid. Chain of carbons. And so on and so forth. There are some hydrogens involved, but we don't really care. Okay? Every time in the reaction of beta oxidation, you chip two carbons away. Does that make sense? And every time you chip two carbons away, you produce a molecule of acetyl-CoA. Are we clear? Say you have 18 carbons in the molecule of fatty acid. How many acetyl-CoAs are you going to produce? 9. We have 3 molecules of fatty acids. It's going to be 27 acetyl-CoAs per 1 molecule of triglyceride, which is a lot, considering the fact that 1 molecule of glucose gives you 2 acetyl-CoAs. Does that make sense? Can you see that lipids are much more energy dense? Okay, they carry a lot of energy in those free fatty acids. We're clear. Now, where does acetyl-CoA go in the carbohydrate thing, metabolism? Krebs, yeah, it gets into the Krebs cycle, remember? Here, Krebs cycle. Gets plugged in there. That makes sense. So what you essentially end up with is glycerol gets into the glycolysis, and products of beta oxidation of lipids, which happens in mitochondria, right there, right next to Krebs cycle, they end up in the Krebs cycle, acetyl-CoA. Okay? Now we know enough to talk about sort of a collective metabolism of lipids and carbohydrates. You're going to get tired of this carbohydrate metabolism, but I'm going to remind you again. Okay? Glycolysis is the breakdown of glucose to pyruvate via the 3-carbon intermediate. Does that make sense? Do you follow me so far? We good? Perfect. Awesome. And pyruvate is converted to acetyl-CoA during the transition step, and acetyl-CoA ends up in the Krebs cycle. And what happens next, we don't really care. We good? Now, what about lipids? Say you consume enormous amount of fat, okay, in the form of triglycerides. Fat is broken down right here. Fat is broken down to glycerol and fatty acids. Okay? Fatty acids feed the reaction of beta oxidation, getting into acetyl-CoA. Glycerol gets plugged into the glycolysis. Blue lines represent what happens during the excess of lipids, okay, when you consume a lot of lipids, during the reactions of lipolysis. Am I clear? Let's admit, the average folk we usually eat fairly balanced diets, which are usually quite rich in carbohydrates. Okay? Makes sense? Like, my wife on Friday brought a whole tray of delicious cake. So I ate very carbohydrate-rich diet for like the entire evening. So you consume a lot of carbohydrates. Glucose. What happens to glucose first? We just talked about it. glycolysis. And the ultimate result of glycolysis is the molecule called ATP. I mean, water, CO2, yeah. But I mean, no, you're good. You're absolutely right. I need to be more explicit in what, but ATP, right? That's your energy. And you got ATP storage full. Not storage, but levels. Levels are high. ATP levels are high. What's going to be the next process that's going to be up? You still, glucose keeps coming, just keeps coming. Glycogen is going to be synthesized, right? So get glycogenesis up. Are we clear? Your glycogen storage capacities are top. Liver, muscles. Glycogen storage is full. Glucose keeps coming. What you going to do with it? You're going to make fat. How are you going to make fat? Nope. Well, lipogenesis, yes, but what are the reactions? You're going to take glyceraldehyde 3-phosphate. I'm going to make it like dark blue. Okay? And you're going to convert it into glycerol. And then you're going to take acetyl-CoA, which is enormously abundant. Okay? And you're going to convert it to fatty acids. Does that make sense? And since you constantly remove the products of glycolysis, products of all this glucose breakdown reactions, you remove glyceraldehyde 3-phosphate, you remove acetyl-CoA, the whole process keeps going. It kind of stimulates glucose utilization. Does that make sense? You constantly take it out. Imagine like, I'm making cars, okay? Just easy. I'm making cars. Usually people buy cars to drive them around. Okay, so I make like 1 million cars a year. And I sell all 1 million. It turns out that some people buy like 900,000 of those cars to just destroy them, just for fun, just destroy them. They throw them off the buildings, okay? Do I care? I don't. My cars are selling, that's fine. I don't really care what they're used for. So for this reaction, it doesn't really matter where acetyl-CoA goes. What happens to glyceraldehyde 3-phosphate? Nobody cares. Does that make sense? As long as they're being utilized. So when you produce glycerol and fatty acids, they can combine into triglycerides, and triglycerides will be stored. Does that make sense? Do you understand? Yes. So the purple arrows, you see the purple? The purple arrows show what happens during lipogenesis. Yeah, this one shows just where triglycerides are coming from. What is the source? But yeah, triglycerides are going to be stored as the fat. Yeah. So basically, look at this, and then it actually explains the whole obesity epidemic in the United States. We discussed last time that if you remove fat from the food, you're left with a lot of carbohydrates. You can get only so much glycogen. And all extra carbohydrates, they're going to be converted to fat and stored as fat. Does that make sense? Now, the question is, how can you lose weight? Eat a lot of fat, which sounds totally counterintuitive. Not just losing weight. I mean, you can just starve yourself. It's a viable option. But if you want to lose specifically fat, you start eating fat. Because what happens? Let's see what happens when you start eating fat. And it's absolutely fascinating from a biochemical standpoint. So let's imagine for a second, okay, that your diet is extremely carbohydrate poor. So you excluded all sugars, you excluded all starch, you receive your fibers from basically cruciferous vegetables, and to make it more fun, it's going to be cucumbers and celery, okay? Celery, some scientists suggest that they have negative caloric value because of all the troubles you go into digesting them. But you eat a lot of chicken, turkey, meat of all sorts, and fish. Forget turkey. You eat lard, okay? Just lard. Just to simplify, pretty much lard is your diet. So you have no carbohydrate intake. So this is gone. Do you still need glucose? Your body, your organs. Yes. Brain still needs glucose. So when you start eating fat, the only viable source of glucose turns out pyruvic acid. Does that make sense? Another viable source of glucose, as it turns out, is oxaloacetic acid, which is right here in the crabs, can be converted to pyruvate and then to glucose. And you ran out of glycogen already. You're done with glycogen, okay? So basically, what happens is you start breaking down fat. The fat that you eat and the fat that you store. Obviously, to lose fat, your caloric balance should be negative, ideally. Does that make sense? You should consume a little less than, you should eat a little less that you spend, okay? So what's going to happen is your triglycerides are going to be broken down into glycerol, which will be converted to glyceraldehyde 3-phosphate, which can become glucose. Your fatty acids will be converted to acetyl-CoA. Turns out, acetyl-CoA can become pyruvate, can be used for pyruvate synthesis, or citric acid synthesis, many other metabolites. But the point is, your fat storage starts to run out, which is pretty much what we try to, right? There's one little sort of a downside. Our whole discussion was built on the premise that some acetyl-CoA that you produce from fatty acid beta oxidation can go to Krebs cycle, right? However, when your carbohydrate intake is extremely low, oxaloacetic acid is used for gluconeogenesis. Does it make sense? Let this idea to sink in. Oxaloacetic acid is used for gluconeogenesis. Let me go back for a second and remind you where oxaloacetic acid is. This is oxaloacetic acid, and it is supposed to combine with acetyl-CoA. Correct? What if you don't have oxaloacetic acid anymore? Can it combine with acetyl-CoA? No, it can't. So what's going to happen to the levels of acetyl-CoA as it is produced from fatty acids? They're going to go up, right? Acetyl-CoA is going to accumulate. But the problem is Krebs cycle isn't running. You do not produce electrons. You do not feed your electron transport chain. You do not produce ATP. So you got to do something else. And liver kicks in and starts making ketone bodies. From acetyl-CoA, ketone bodies are made. They're made in the liver. And these ketone bodies, which include acetone and acetoacetic acid, they can be used as the fuel by practically any cells in the body. And this state is called ketosis. Now, this is something, so let me sum up so far. You do not eat carbohydrates, right? Since you need a glucose Fat is broken down to glycerol and fatty acids. Glycerol is used to produce glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate will be used for the glucose production, right? Oxaloacetic acid will be used for glucose production as well, which obliterates Krebs cycle. Now, what you have is fatty acids that are oxidized to acetyl-CoA, and acetyl-CoA has nowhere to go, and it's accumulated, and when it's accumulated, liver starts to convert it to ketone bodies. And ketone bodies can be used as the fuel by practically all the cells of the human body. Okay? Does that make sense? What are the downsides or upsides? I'm talking about dietary ketosis. Okay? You're going to produce a lot of acetone. Your breath is going to have a little bit of flowery smell, which is not bad, really. You're going to have no glycogen storage whatsoever, obviously. And when you enter the stage of ketosis, you feel tired, very tired, all the time. I didn't get quite that far in my personal experiments, but I've got pretty low, and it was terrible. And you consciously understand that you can move, that you're not really tired, that you have. I had enough endurance to make pretty long runs. Like, I wake up tired, I go on the run tired, I run, I'm tired, I'm always tired. Okay? Generally, to get into the ketotic state and get used to it, to get adapted to it, it takes about a couple of months. Okay? It's individual, it depends. If you're really dedicated, after a couple of months, according to people who did that, it gets better. There are ultra runners, run 50, 60 miles. They do it in ketotic state. The upside of generally, if you are an endurance athlete and you run or bike for a long periods of time, you have certain gels or pretzels or something to give you glucose on the run, because your cells are sort of, for them, normal metabolism, glucose-based metabolism. People who are in a ketotic state, for them, glucose is not necessary. So they can have a pretty good fatty, very fatty meal before, and they can run for hours and hours and hours without any fuel source. All they need is water to, let kidneys to get rid of metabolites. Does that make sense? Now, dietary ketosis is normal and healthy. By normal and healthy, I mean it doesn't take a toll on your kidneys, it doesn't take a toll on your brain, unless you do it extremely fast. There are examples what can happen in people, the bodybuilders, if they try to reduce the water content and get into ketosis. At the same time, they do not have enough fluids to remove acetone and acid that is formed, acetoacetic acid that is formed. And they go not just in ketosis, but so-called ketoacidosis. Acidosis, decreased blood pH, leads to the depression of neuronal activity, which may lead to coma. Usually it leads to, if it doesn't lead to coma, it leads to very serious confusion, mental confusion. Now, people with type 1 diabetes, when they do not take insulin, what happens to glucose? Where? Where it goes up? In the blood. Why does it go up? Don't tell me because they have no insulin. Which process is not working? Yeah, so glucose stays high in the blood because it doesn't get into the cells. So cells basically have no glucose. Since they have no glucose, what do they have to use as a fuel? Fat. When they break down fat, they get eventually ketone bodies like liver and all that kind of crap. Okay? Now in case of type 1 diabetes, that process is not controlled, not well controlled. That makes sense. pH drops precipitously, very precipitously, and that shuts down the brain. That makes sense? So basically, high fat, low carbohydrate diet is good. It sucks in terms of day-to-day experience, but it's good for losing fat. And you know, if you looking at, I don't know, any of the NFL athletes and want body like that, keep it real. You have to exercise like 6 hours a day and eat very balanced meal and do nothing except that. So, you know, it's not real. But losing weight, yeah, it allows you to lose weight very fast. And it's good losing weight, you know, your fat goes away. And the first fat that goes away is abdominal fat. Subcutaneous fat goes away the last. It's going to hang out for a while. Does that make sense? Questions? I'm going to be very upfront. These changes, yeah, I'm going to ask you about those. I will show you the sort of a final, we will try to picture the final scheme, the flow chart, and you have to be able to produce it by yourself and understand it. Now we've got fats, we've got carbs. Let's talk quickly about proteins. So in the protein situation, you have amino acid. Okay? The first step of protein metabolism is so-called transamination. When amino acid and alpha-ketoglutarate acid swap the functional groups, and you have keto acid and glutamate. So, what can happen next? So glutamate, this one, can be completely deaminated, complete deamination, pretty much breakdown. When glutamate is deaminated, you end up with urea, okay, and alpha-ketoglutarate acid. Urea is removed from the body with the urine. You also produce CO2. CO2 is exhaled. And keto acid that's produced here can enter either Krebs cycle, okay? There are several keto acids there, oxaloacetic acid, alpha-ketoglutarate acid, or succinic acid, or it can become pyruvate. Basically, what you need to understand is that in regards to proteins, products of protein metabolism can be either destroyed in the deamination, or after transamination can become pyruvate or enter the Krebs cycle. That's as much as I want you to know. Are we good? Now, cholesterol. Cholesterol is critically important for your body. It's a part of the membranes. It is the source for vitamin D synthesis. It is the precursor for all your steroid hormones, from aldosterone to cortisol. And you know what's interesting? You make 85% of cholesterol from acetyl-CoA, which means only 15% of cholesterol that you need comes from the diet. without even getting in the details, if only 15% of cholesterol comes from the diet, can you significantly alter your cholesterol levels by eating cholesterol-rich products? Unless we're talking about 30 egg yolks a day, then no. Multiple studies demonstrated that dietary cholesterol has little effect on the ratio between low density and high density lipoproteins. To understand why this ratio is important, we need to address the cholesterol transport in the cells, in the body. So when you consume cholesterol, it's fat. Where does it go from intestinal lumen first? It's not blood, it's lymph, right? And lacteal. Eventually, as chylomicrons, the part of chylomicrons, cholesterol will end up in the blood and will make its way to the liver. And in the liver, cholesterol, remember it's a fat, it cannot travel alone. It will be packaged in the so-called lipoproteins. This is the letter L in these acronyms. Liver makes very low density lipoproteins and low density lipoproteins. If you would look at the composition in the very low density lipoproteins, main component is triglycerides, good chunk of phospholipids and cholesterol. In low density lipoproteins, the main component is cholesterol. Does that make sense? The one component that I did not mention is protein. About 10% in VLDL and 25% in LDL. I want to explain you the physics of the names. If you would compare the density just from your own experience, density of the fat, like solid fat, and density of the solid protein, which do you think is higher? What is lighter, muscle or fat? Fat. People who have very little fat have hard times holding themselves in the water surface. They sink because they don't have enough flotation. Does that make sense? What happens if somebody has absorption problem and fat isn't getting absorbed in the intestine and gets out with the feces? What happens with the feces? And they float. It's called steatorrhea. When feces float, they float because of the high fat content. If they have very little fat content, oh yeah, they will sink. They will sink all right. That makes sense. So this very low density and low density lipoproteins have a lot of fat and very little protein. That's why they're low density. And that makes perfect sense because what they do, they transport fat from the liver to the tissues. So fat goes from liver to tissues. Okay, that's low density. Because they transport fat. Does that make sense? What happens in the tissues? What happens with fat in the tissues? What is it transported for? What's the purpose? What does it provide? Energy, or, sorry, if it gets to the, fat, storage, right? It's either storage or use. So tissues will take the fat away. Do they take all fat? No. They will send some back to the liver. That makes sense. And they will send it back in the form of high-density lipoproteins. And high-density lipoproteins, they have high density because they have a lot of protein and very little fat sent back to the liver. Does it make sense? That makes sense. So basically, total cholesterol level in the blood generally is a very poor predictor of cardiovascular disease. Do you understand what I just said? You can measure total cholesterol. This, and this. Okay? These three together. You can measure these three. But this parameter is not really important. What is important is the ratio of HDL to LDL and VLDL. What do you want to be high? HDL. You want HDL to be high. You want to have a lot of high-density lipoproteins because it means that tissues are very effectively utilizing fat. One, okay, that's number one. And number two, if you have constantly a lot of low-density lipoproteins circulating around, there's better chance for these molecules to be scavenged by macrophages. When macrophages scavenge fat, they become so-called foam cells. And they reside in the walls of your blood vessels. And when they scavenge fat, they start to produce inflammatory molecules. And they start to attract to themselves white blood cells. And white blood cells produce even more inflammation, and platelets perceive this inflammation as the injury. They start to try to clot. And they try to clot where there is no injury. So eventually what is formed is a thrombus. And this thrombus, eventually what is formed is atherosclerotic plaque because it consists of fat, foam cells, white blood cells, and platelets. And this atherosclerotic plaque is sitting there blocking your blood vessel. If you want to compare how your heart feels pumping through sclerotized blood vessel, take 2 straws, one regular and one coffee stirrer, and try to sip through each. It's really different. Does that make sense? Now, when you will now go to the doctor, the physician, and will ask for the full blood workup, they will give you HDL to LDL ratio, or LDL to HDL, whatever it is. And you want a lot of HDL and as little as possible of LDL. I don't remember the clinical numbers for it. I mean, you can look it up. Basically, the idea is that dietary cholesterol does not really affect this ratio unless you go completely insane. Like you start eating pork 5 times a day. I'm talking like a gigantic pork chop. Like you consume enormous amount of saturated fat every day. Then yeah, it's going to affect your dietary. And it's mostly saturated fat. Does that make sense? Now, all these cholesterol-free products, if you maintain balanced diet, they're not going to affect your dietary cholesterol, your blood cholesterol. Whether you like, if you like good butter on your steak, it's fine. Unless you do it 5 times a day. And we're talking, and you do like stick of butter on like 12-ounce steak 5 times a day. Okay? Then you're probably going to have some effects on your cholesterol. Other than that, you should be fine. That makes sense. And as you can see, dietary cholesterol makes no significant contribution to atherosclerosis and risk of cardiovascular disease. Again, I am talking about reasonable stuff. Like, I scared the living daylights out of you talking about diabetes, you know. And I told you about the temple of diabetes. But if you go to Cheesecake Factory and order one dessert there, it's not going to give you diabetes tomorrow. Okay? And probably like if you do it once a week, it's not going to give you diabetes. But if you do it every day for a month, yeah, you're probably going to get it. Does that make sense? So, I don't want to sound like your grandma saying that everything is good in moderation. But really everything is good in moderation. Okay? Unless you like professional athlete, then it's totally different thing. So this is pretty much the flow of metabolism that I want you to appreciate. Carbs. I'm going to highlight the key steps. Glucose. Via glyceraldehyde 3-phosphate is broken to pyruvic acid. Pyruvic acid is converted to acetyl-CoA, which enters the Krebs cycle. If ATP levels are high, glucose is going to be converted to glycogen. If glycogen storage is up, its capacity is filled, okay? Acetyl-CoA is going to be converted to fatty acids. Glyceraldehyde 3-phosphate is going to be converted to glycerol. And they're going to combine in the process of lipogenesis. They're going to make fat. Does that make sense? Now, if you are in the state of starvation, you have no carbohydrate input whatsoever, but you have a lot of fat, triglycerides is going to be broken down to glycerol and fatty acids. Glycerol will become glyceraldehyde 3-phosphate, which will be used to produce glucose. Fatty acids will be metabolized to become acetyl-CoA. This is the reaction of beta oxidation. Okay? Acetyl-CoA can enter the Krebs cycle, but if oxaloacetic acid from Krebs cycle is gone, acetyl-CoA has pretty much nowhere to go and converted to ketone bodies in the liver. At the same time, probably, amino acids are going to undergo transamination first, and then glutamate will be deaminated, being converted to urea and carbon dioxide eventually. And keto acids can enter, there's a little bit of a trick here, can become pyruvate, converted to pyruvate, or they can enter the Krebs cycle. Does that make sense? We're good. Okay. Now, that actually brings up a lot of, a lot of questions. So, like, a general question. If you want to get rid of the fat ASAP, low carbohydrate, high fat, moderate protein diet. Protein to maintain the lean muscle mass. I think you asked me last time, right, Alex? So yeah, but if you want to muscle build up, you have to provide enough. You cannot run on the negative caloric balance and hope to build up muscle. It's not going to happen. Some of the protein, structural protein, will be used as the energy source. To build up muscle, you have to provide enough energy, either in the form of fats, but what's more common, in the form of carbohydrates. So if we would look at the diets that pretty much designed to provide the muscle buildup, basically all these diets include a significant portion of carbohydrates to spare proteins from being used as the energy source. What happens when you starve? Glycogen goes first, and then it's not going to be fat and then muscle. No, you're not going to get lean and skinny and look like Ryan Reynolds, in any of his movies, and then you're going to start losing muscles. No, these two things are going to happen together. You're going to lose fat and muscle when you starve. Does that make sense? No. Now, absorptive versus post-absorptive state. So absorptive state is what happens to you after the meal. So, you eat, okay? Food, blah, 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 goes through the mouth and stomach and ends up in the intestines. And in intestines, you have an absorption, right? And you absorb amino acids, glucose, and glycerol and fatty acids. Okay, we good? That's what you get as the nutrients. Absorption increases. You have a lot of glucose, a lot of amino acids, a lot of fatty acids and glycerol in the blood. Okay? You have to use them. So anabolism, synthesis, will dominate. Am I clear? For amino acids, they will be metabolized anabolized to proteins. They will be used to make proteins. Glucose, ATP, but then glycogen. Free fatty acids and glycerol to make triglycerides. Okay? Does that make sense? Fat will become VLDL, so fat will go to adipose tissue. Okay? Liver and muscles and fat tissue, they will use mostly fat as the energy source. Other cells will use carbohydrates mostly. Okay, brain will use practically only. And in absorptive state, brain will use only glucose. Amino acids. If you have excess of amino acids, some of them will be converted to fat. Does that make sense? You have to understand that it's not like you have a lot of little tiny people sitting in different organs and sorting molecules out. It's not going to be, okay, this is amino acid, this is for protein synthesis. This is glucose, this is for energy. This is free fatty acid and glycerol. We're going to put them together and send them to the fatty tissue. Now, some of the proteins will be used as the energy source. Some glucose will go into the glycolysis, some glucose will go into the lipogenesis. It's inevitable. But we talk about what dominates. Does that make sense? But most proteins that are consumed during absorptive stage, they will be, most amino acids that are consumed during absorptive stage, they will be used for protein synthesis. This is sort of the same schematic, okay? So glucose, glycogen, or ATP synthesis, or triglycerides, Remember we talked about this, how glucose can be used for triglyceride being formed via lipogenesis from glyceraldehyde 3-phosphate and acetyl-CoA, glyceraldehyde 3-phosphate to glycerol, acetyl-CoA to fatty acids. That's that. So glucose can be used for glycogen synthesis, ATP synthesis, or fat synthesis. Okay. Triglycerides. Storage. Just storage. Just think about this. Fat will be used storage. Proteins. Amino acids. Protein synthesis, or some of it is going to be used for ATP synthesis. So this is the challenge that you face when you study, especially metabolism. The challenge is everything happens. Everything. But the question is, which processes are dominant? Okay? So we can say that in absorptive state, what's going to be the primary source of energy? Carbohydrates and fats. What is going to be the primary use for amino acids? Making proteins. Is that going to be the only use? No. But the primary, yes. Good? Now, insulin and absorptive state. Insulin regulates absorptive state, really. That's it. You know. High glucose, high amino acids stimulate insulin. Insulin increases uptake of amino acid and glucose. Amino acids, when they get into the cells, they will be used for protein synthesis. Glucose will be used to make glycogen, fat, and ATP. Does that make sense? So it is called hypoglycemic hormone because it reduces blood glucose, and also insulin is technically anabolic hormone. Insulin does stimulate protein synthesis. Does that make sense? Are we clear about it? Good? Cool? Okay. Post-absorptive state. Like, totally opposite. Like, I don't know. If you didn't have lunch yet, I hope you did, but if you didn't, and only meal that you had was breakfast, you are in the post-absorptive state. What it means for you. I'm going to talk priorities, okay? So glycogen first. Glycogen is broken to glucose. Good. Triglycerides, in the process of lipolysis, broken to glycerol and fatty acids. Fatty acids will be oxidized to acetyl-CoA. Glycerol will enter glycolysis. If it's not enough, only if it's not enough, protein will start to break down. Okay? Does that make sense? What you're going to use as the source of energy, I'm telling you, glucose and fatty acids. Ketone bodies if you run out of glucose completely. If all glucose that goes synthesized gets to the brain. This is called sometimes glucose sparing. When cells of the entire organism, except for the brain, switch metabolism to metabolism of ketone bodies. So glucose can be spared for the brain. Does that make sense? Now, the good example, by the way, the good example of how effective this switch is, brain is largely dependent on glucose for its function. And when it wasn't, again, I don't say it was ketosis, but it was darn close to it. I didn't get dumber. I didn't become a slowpoke. Because, yeah, every cell in my body was using mostly, ketone bodies. But whatever carbohydrates were available, they were channeled right here. So I was still okay in terms of thinking. Does that make sense? The brain is extremely metabolically active. I mean, if you really, really do a lot of thinking, a lot of studying, you have munchies. Because your carbohydrate source is being exhausted very fast. Your brain works hard and it uses a lot of glucose and your glucose levels go down and you feel hungry all the time when you study. And that's normal, that's physiological. Does that make sense? Amino acids in the liver will be converted to glucose. Okay? Because you're starving. Glucose, there's no exogenous glucose coming in. So your body tries to produce glucose. This is pretty much the opposite. So look, in the muscles, glycogen is converted to pyruvate. Pyruvate is converted to glucose. Protein is broken down to amino acids. Amino acids are broken down through keto acids to make glucose. Fat converted to glycerol, glucose. Fatty acids by ketone bodies for ATP. Fatty acids, ketone bodies, glycerol, again ATP. So glucose will be used for ATP synthesis basically only in the brain. And what regulates this process? Glucagon, right? So low blood glucose, low blood amino acids. Plasma glucagon goes up. Liver, via glycogenolysis and gluconeogenesis, increases plasma glucose. Adipose tissue is broken down, fat is broken down. Either glycerol and free fatty acids will be used as the energy source, or ketone bodies. So essentially, glucagon is the hormone of fasting, is hyperglycemic hormone. Interesting deal, though, is that there are other stimuli that will induce the same effect. First and foremost, sympathetic activation. Sympathetic activation, which is basically exercise, has similar effect on the endocrine system as the elevated glucagon. Does that make sense? It will promote breakdown of fat, it will promote breakdown of glycogen, and so on and so forth. In case of high protein, the effect is really interesting because high protein, low carbohydrate. So carbohydrates are low, right? Glucagon has to go up. You see, you consume low carbohydrate meal, your blood glucose is low, okay? Glucagon goes up to increase blood glucose. But at the same time, you have high amino acids. High amino acids stimulate insulin. Insulin increases amino acid uptake. So that specific kind of meal will induce both hormones. Does that make sense? Now, that's, okay, before we move to this table, which is more of an overview, what you need to understand about absorptive, post-absorptive state. I'm not going to ask an enormous number of questions about those. I'm going to ask core questions. By core questions, I mean, which hormone regulates which? Insulin is the hormone of absorptive state. Glucagon is a hormone of post-absorptive state. Which processes are dominating? Anabolism in absorptive state, catabolism in post-absorptive state. I'm going to ask you, what happens to proteins in post-absorptive state? Proteins are broken down to amino acids. In absorptive state, proteins are synthesized from amino acids. That makes sense. What happens, which processes in absorptive state are up? Everything genesis, lipogenesis, glycogenesis, not gluconeogenesis, glycogenesis, lipogenesis, glycolysis. Which processes are up in post-absorptive state? Lipolysis, gluconeogenesis, making glucose from scratch, glycogenolysis. Very basic stuff, okay? Seriously, like very, very basic. But yeah, I'm going to ask this, okay? And the question, I can tell you it's not a problem, it's not a cheating. I can tell you, What happens in absorptive state? You have 4 answers, 5 answers. You have to pick what does happen in the absorptive state. It can be a combination. I can ask, okay, what happens in the absorptive state? And if you start reading an answer and it says absorptive, okay, I said absorptive. It says glycolysis. Does it? Yes, it does. It does happen in absorptive state. What's the next? Lipolysis. No, it's not. No, it's not happening. Glycolysis does. Lipolysis doesn't. No, it's incorrect. Move on. Does that make sense? Yes, I will ask you a lot about upregulation of those things. Be very comfortable with these terms. Am I clear? Okay, good. Anabolic versus catabolic hormones. Anabolic hormones, the most important ones, I would say. Insulin, growth hormone, and thyroid hormone, and testosterone, which makes perfect sense. Growth hormone, it's damn growth. Okay. Testosterone and estrogen too stimulate growth of muscles and bones. Okay. Insulin increases the uptake of amino acids. If you would look at the performance enhancement drugs, especially in bodybuilders, it's insulin and testosterone derivatives. Growth hormone isn't that popular due to the really widespread effect. I mean, it's dangerous, more dangerous than, I'm not saying that it's safe at all, but growth hormone is dangerous. Okay. Thyroxine, also not really good idea to take thyroxine. It messes up the entire HPT axis regulation. Classical catabolic hormones, well, cortisol, basically catabolic, the only one, because cortisol directly affects the breakdown of proteins. It increases the protein breakdown. That makes sense. But you can technically say that glucagon, epinephrine, they are catabolic in regards to, say, fat storage. They break down fat. Does that make sense? Now, last little bit. If you probably are bored to death about my examples from running. If you run or you do any other type of endurance activity, that includes bike races and triathlons, most of the, well, if people are normal, then the good race is on Saturday or Sunday, but Saturday is preferable. And usually what happens night before, the company that organizes the race, they often offer the pasta dinner, also known as carb loading, which is partially a scam. Because if you just maintain your normal regular diet, then if you, like normal, you run, I don't know, you're about to run a half marathon, your normal daily routine involves 4 or 5 miles, you run like 10 miles in the weekend, and you just eat normally, and then you come on Friday night and you devour a gigantic bowl of pasta. So you load your gastrointestinal system with a lot of carbohydrates. Where are they going to go? First. First. Carbohydrates, glucose. First. Glycogen. But look, you are on your normal diet. Your glycogen storage aren't exhausted. Unless you ran 2 marathons 2 days before that. So very little of it will be stored as the glycogen. The rest, sorry, you're going to store it as a fat. So for carb loading, what some runners do, about 2 weeks before the race, they go on extremely low carbohydrate diet. okay? The glycogen storage are completely exhausted. And what is it? I mean, it's sort of an anthropomorphic thing, but think about this. Pretty much your biochemical systems, they kind of, okay, we need glucose. What about glycogen? Oh, damn, we ran out of it. No? Still no? Okay. No glycogen? No. Okay. No. And then on Friday night, you flood it with glucose. An interesting thing is that glucose abstinence for 2 weeks temporarily increases your glycogen storage capacity. So you accumulate more glycogen that you normally can. Does that make sense? Kind of your biochemical response, oh crap, I have so much glucose, let's stuff the pantry. So when you go on the distance, you have more than regular amount of glycogen, so you hit the wall later. The problem with that approach, you're going to hit the wall anyway. So runners that do ketosis, they don't have that problem at all, because they do not rely on glycogen at all, absolutely zero. They don't have to do carb loading. They do not have a wall, which is quite interesting. It requires, a lot of work, but kind of an interesting detail. Okay.